아, I should have got my phone.
Oh. Okay, howdy. So, okay, I share the screen. Oh, give me a second. Okay, so yeah, as you know, next exam 3 score is uploaded in the eCampus, and I will disclose the exam 3 in the website. Yeah, in today, later today. So this is because there is some students who need to get the macro exam. So yeah, I will give him macro exam in this 3 p.m. So maybe for at the 5 p.m. You will see the result on exam 3, and I will also disclose the grading scheme. So please check the result using. Is audio bad?
The audio sounds real bad.
So you cannot hear this audio well, right? Okay, let me change my.
It sounds robotic.
Is it okay?
No, still sounds the same.
Okay. Is it okay? Can you hear me? Okay.
Yeah, no, we can hear you. The problem is you sound like a robot. So
Sounds like a robot. Oh, all right. I don't know how to deal with this. Oh, I have one. Okay, I have one way. Give me a second. Now, can you hear me? Is it good? Great. So, okay. So, Ijan, give me a second. I just. Can you hear any echo?
Oh, that fixed it.
Okay, so everybody in the classroom, can you hear my voice at this point? Right? Okay, then can you hear everybody in the Zoom class? Can you hear my voice too? Okay,
Yes.
then let's read this. Okay, so yeah, today I will just go to the Big3 auctions, and as I said in the email, I will give you exam in 3 p.m. So please give me a second. So okay, so in the Big3 auction, so bidders independently submit their sealed bid, which means that they just give the some do not disclose their bid to others, and the winner is the highest bidder, but he or she will pay only the amount of the second highest bid. So for our example, we will assume that ties do not occur, right? So for example, if there is 4 people who are bidding for tickets to the musical, and Jane bid at $8, Carlos bid at $100, and Gary bid at $110, and Amit bid at $120. Then the winner is Amit because his bid is the highest bid among all others. But how much does he or she need to pay for big ticket is just only $110 because Gary's bid is the second highest bid, right? So that's the Big3 option. So, and it is actually used for eBay. So when you bid for in eBay auction, then if you got your object, then you will only pay the second highest price from that object. So let's see some example about the eBay example. So Sherry, John, and Andy are bidding on the painting on eBay. So minimum bid was set at $50, and the sorry, it's typo, and the bid increment is $2. And complete the following chart to show the progress of the auction before time ran out. So here, Shirley first bid at $50, and then John suddenly bid at $2,000. That's a little bit, kind of sudden X, but yeah, in that case, even if Sherry bid at $60, or Andy bid at $80 or Sherry bid at $120, but still, in that case, John will take it, right? But at this point, current winner is John, because so after, yeah, if you're just thinking about only 2 bids exist, Sherry and John, then current winner is John, but he only needs to pay the $50 and this increment in $2. So he needs to pay at $52. right? Because yeah, increment is already happens at the $2, so that's why he need to pay. And after getting a Shirley bid again, Shirley bids at $60, but still current winner is John because John suggested $2,000 already. But at this point, the second highest one is just Shirley's one, so which is $60. So it is $60 plus $2 increment. So eBay bid is $62. And in case of Andy bid at $83. But yeah, so in that case, still John is winner because John's $2,000 is the greatest among all other bids. But what he needs to be paid is $83 plus $2, which is $85. And lastly, Shirley bids at $120, but still $2,000 is greater than $120. So John's bid is $120 plus 2, which is $122. So in this auction, John definitely will win the auction, but how much did John for the painting is $122. So this $2 is just like a kind of commission or fees for this auction. So that's the Bakery auction, right? Okay, do you have any question on Bakery auction? Okay, then let's deal with the chapter 14. So chapter 14 is about the apportionment. So this apportionment problem is related to kind of politics. So because in the United States is actually start with 13 states, right? But right now we have 37 other states here, so they are added. So they need to make some portion for each state on the House of Representative and Senator, right? So to deal with it fairly, so a lot of politicians and mathematicians think about this kind of apportionment problem. So we will just deal with some kind of the way of to be fairly distributing seats in the House of Representatives among all others, right? So first of all, let's see some example. So, okay. So there is some university here, and they wanna create the student government with 16 representatives from 4 groups of students. One group is freshmen, the other is sophomore, the other is junior and seniors, right? And if we desire that each representative represent an equal number of students, how many representatives will each class have, right? So maybe one of the way you can think about it is just divided by portion of their population among all others, right? So here, the total population is, if you add all the number of students, then you got 13,000. So maybe, and their portion in the freshman portion among all other students is 20,000 over 32,000, which is what is this? But it is 20 over 32. So if you just divide both sides by 4, you can get 3 over 8. But we have only 16 representatives. So if you just multiply these numbers, 3 over 8 times 16, then their portion is 6 representative, right? And in case of sophomore, their portion among all other students is 10,000 over 32,000.
So it is 10 over 32 and divided by 2 for both numerator and denominator, you can get this is 5 over 16. But in that case, 5 over 16 times 16 is 5 representatives. And in case of junior, their portion among all population is 6,000 over 32,000, which is 6 over 32. Then if you just divide both sides by 2, then you can get it is 3 over 16. So 3 over 16 times 16 is just 3. And in case of senior, it is 4,000 over 32,000. And this is the same as 4 over 32, but it is equal to 1 over 8. So 1 over 8 times 16 is 2 representatives, right? So in that case, if you add all the representatives, 6 plus 5 plus 3 plus 2, then it is your 16. So you are fine, right? So in this case, yeah, you can see that it is kind of equal apportionment for representatives. So here we have some terminology on this apportionment problem. So here the house size is the number of this total population, right? Is the total number of, sorry, house size is total number of representatives. So in this case, 16, right? And the standard divisor is the total population P. So P is here the total population divided by house size. So S is P over H. And the group's quarter, QI, is the group's population, PI, divided by standard divisor. So QI is PI of S. So this is terminology devised from the, the Congress. So let's see why these numbers are happening. So, okay, so here, if you think about this S in this case, in this example, S is P over H, but P is 332,000 and 16 is outside. So it is 2,000, right? And if you just divide your population by 2,000, then you get the same result in here because, for example, 20,000 over 2,000 is just 20 over 2, which is 6. And 10,000 over 2,000 is, which is just 10 over 2, which is 5. And 6,000 over 2,000 is 6 over 2, which is 3. And 4,000 over 2,000 is 4 over 2, which is 2, right? So this number is exactly the same as this number. So what we did as a standard divisor is, so if you think about this number, how this number consisted, then this is the population representative, number of representative is just population of a group divided by total population multiply the house size, right? So that's the formula we used for this calculation. So we just divide the population of a group by the total population and multiply the house size, right? But in the terminology in here, this total population is P and house size is H. and population of the group is pi. So you can just simplify it as pi over p times h, right? And then from simple mathematical, thinking, you can see that it is just rewriting it as h over pi, right? H over p. Then now you know that S is P over H. So this is the same as Pi divided by S because this is 1 over S, right? So that's why the same equation in the green is the same result with equation in the black, right? So to avoid such a, second, 2 times of calculation, we just find the standard divisor first and just divide each population by the standard divisor to make it simpler. Okay, do you have any question on this method or terminology? So in usual case, to make the apportionment problem, you need to find the standard divisor and divide the population of each group by the standard divisor to get the number of representatives in house. So that is the way we use. Okay, is it good? Okay, then let's deal with the same example. But at this point, we already have 15 representatives instead of 16 one, right? In that case, first of all, your standard divisor S is population divided by house size. So it is 32,000 over 15. And 32,000 over 15 is, what is that? Is approximately it is 2,133.333, right? So you can rewrite it as 3 with infinitely many threes in the decimals. So in that case, your representative number is divided by S. So it is 5.625 if you use your calculator, and 10,000 divided by S, this 2133.333, you can get it is 4.6875 if you use just, this number. And 6,000 divided by standard divisor is 2.8125. And 4,000 divided by S is 1.875. So in this case, if you add all the numbers, then total number is 15. But there's one problem that there are no person with, only decimally existed, right? So you cannot divide a person with decimal point, right? So there is no person with 0.6 to 5% or something like that. So in this case, we definitely need to round the numbers or round down some numbers to do this. But the problem is that, so for example, so if you are from California and someone is from Texas, and so then definitely if your number goes down and your California's number goes up, then Texas people do not like it because their representatives have the smaller portion in the Congress. So they need to be paired to do such a, a round up or round down, right? So that's the, so to make such a round up be pair is called apportionment problem. And a procedure of solving apportionment problem without making arbitrary choice is apportionment method. So we will deal with some cases when this kind of problem happens up. Okay, right? Okay. Do you have any question on this example?
You're saying that we would round up?
Okay, so before deal with this kind of apportionment method, let's deal with some notation, right? So here, if Q is some decimal number, which is not integer, and we call it the rounding Q up to the next integer, is called this Q with cell. So here, this is called cell function in math, because it is kind of, if your point is 3.5 and 4 is in your cell, 4 lives in the cell of 3.5. So that's why we call it as a cell function. Or you can round down your Q to the previous integer. It is also called plural function, because 3 lives in the plural of the 3.5. So that's why we call it plural function. Or you can just choose the nearest number, nearest integer, right? In that case, it is just Q with this sign, and it is usually called Gaussian function. You don't need to know the name. I just I just introduce those names which when you read some other math books or other articles. So so if Q is halfway to the next integer or larger, then round up to the next integer, which means that in case of 3.5, 3.5 is half of 4 and 3, but this can be regarded as 4, right? Otherwise, round down to the previous integer. So for example, however, 3.49 with Gaussian function is 3, because 3.49 is less than 3.5, right? And lastly, I just introduced the geometric mean, which is Q star is just square root of the plural times cell functions, right? So for example, in case of 3.5 star is square root of plural of 3.5 times cell of 3.5. So 3 times 4 with square root. So it is square root of 12, which is 2 square root of 3, right? So these are the mathematical terms we use to determine the apportionment method. Okay. Do you have any question on here? Okay, then let's deal with some, examples. So here, 2.5 is the half of 2 and 3. So in case of Gaussian function, sorry, this should be not Gaussian, it is Selling, sorry. Because we have Gaussian in the third row, so it should be Selling. So in case of Selling, it is goes to 3, right? Because 3 is the nearest integer, which is greater than 2.5. But in case of flooring, it is 2, which means round down. Round up. But in case of the Gaussian notation, it is 3. And in case of geometric mean, it is 3 times 2 with square root sign, so which is square root of 6. And if you just think about this square root of 6, then if you're just using your calculator, it is almost 2 point something. So at 2.4494. Sorry. $2.4494. So in the last one, round according to Q star means that if your number is greater than this Q star, then let your number round up your number. But if your number is less than your Q star, then round down your number. So in this case, 2.5 is greater than 2.4494. So it is rounded up to 3, right? Q. Okay, do you have any question? Okay, then let's deal with the example together. In case of 2.45, what is the roundup? It's 3, right? So yes, you round up in the case of Q star, in case of 2.5, but in case of round down, 2.45 is goes to 2, and in case of this Gaussian, it is just round the nearest integer. So it is 2, and Q star is still the same as square root of 3 times 2, which is square root of 6. And we already know that this value. So in this case, 2.45 is greater than 2.4494. So we need to round it up. So you need to get 3 in here, right? And in the next example, you got the same number here. But in case of rounding according to Q star, now 2.44 is less than 2.4494. So in this case, you need to round down, right? And in case of 2.1, then every number is the same, but again, 2.1 is less than 2.4494, so it should be rounded to 2. But in case of 2, rounding up 2 is just 2, right? Because 2 is the integer. So 2 is the smallest integer, which is greater than or equal to itself. And round down of the 2 is just 2, because 2 is integer. And round the nearest integer is still 2, because it is integer. So in this case, it is 2 times 2 is square root sign, but this is the same as 2. So rounding according to 2 is just 2, right? Because it is just itself. All right, then let's deal with 1.9. So here, roundup of 1.9 is 2, but round down of 1.9 is 1. And 1.9 is much more near to 2 than 1. So rounding the realist integer of 1.9 is 2. But in this case, Q star is 2 times 1 is square root sign. So it is square root 2, which is almost 1.414 something. So if you just round according to Q star, 1.9 is greater than this 1.414. So this should be 2, right? And in case of 1.45, it is 2, 1, 2, those are same. And also this Q star is also same, but still in this case, 1.45 is greater than 1.414, so it's 2. But in case of 1.4, everything is same, but 1.4 is less than square root of 2, 1.414, so it should be 1. And in case of 0.6, round up 0.6 is 1, but round down 0.6 is 0. But nearest integer is 1 because 0.6 is greater than half. And Q star here is square root of 0 times 1, but this is nothing but 0, right? So round it according to Q star, it is 1. And you can see the
Professor?
same thing.
Professor,
So
for
just like
1
but in case around this, the nearest integer, it is 0. But Q star is 0, so according to Q, it should be 1. And you can just get the same result in the last part. Right?
Professor, I have a question.
So different apportionment methods will use the different rounding rules. That's why we care about it. Okay, question? Thank you. Yeah. Sorry. Yeah. So what her asked me is that this one should be 1. Sorry about that. Yeah. Because 1.4, 1 is the nearer than 2 with respect to 1.4. So thank you very much. Okay. Do you have any other question? Okay, then let's deal with some example about this apportionment method. So first one we will learn is Hamilton method. So this name came from Alexander Hamilton. Okay, there is just some chat message. Region 1.45 is closer 1 than 2. Thank you, Dawson. Yeah, that also true. Sorry about my typo. Thank you, Joanna and Catherine, to figure out this. Okay, so Hamilton method came from the Alexander Hamilton, who is the first secretary of the, what is that? Kind of secretary of state, maybe? I'm not sure about that name, but he's very famous politician in America. Yeah, so this method is actually, approved by the Congress of US House of Representatives, but George Washington both vetoed this apportionment method, but it was rarely used for in US between this 50s to 90s. So the method is the compute standard divisor first, then compute the quota for each state, then round each quota down. Then you have some portions which are not assigned, right? Then calculate the number of seats that have to be assigned. Then assign the remaining seats to the state with the largest fractional part of Q, right? So let's deal with some example. So let's get back to the university case, which we deal with in the first. So in this case, Q is just came from, so here S is 32,000 over 15. So it is 2,133.663. So quarter is just determined by this, population divided by S to get those numbers. So if you just round the quarter, calculate rounded quarter in the Hamiltonian method, it means that just round down your number in Q. So what you need to get is 5, 4, 2, 1. And if you add all this rounded quarter, then you get 12, right? So from here, you have 3 seated seats are not assigned yet. Right? So in this case, you just see the fractional part for each state or each group, right? And then that's the seniors has the biggest fractional part, and juniors has the next biggest fractional part, and sophomores has third fractional part, and freshman are last. But we already have 3 seats, so just add 1 seat for seniors and juniors and sophomores, then you are done. So here, seniors should be 2, and juniors should be 3, sophomores should be 5, and freshmen 5. Then all 15 seats are assigned for each groups, right? So that's the Hamiltonian method. That is simple, right? Okay. Do you have any question on this method? Good. Okay, so let's deal with one more example. So a school district received 46 computers to distribute 5 high schools based on the number of AP statistics students in each school. So use the Hamiltonian method to distribute the computer. So here, again, the total population is, if you add all the number, then it's 560. So our standard divisor is 560 over 46. And it is almost 12 point something. Yeah, something students per computer. So your quarter is 39 over this S, which is 3 point, yeah, I just pre-calculated it. It is 3.2036, and 71 over S is is 5.8321 something, and 18 over S is 1.4786 something, and 223 over S is equal to 18 over 18.3179 something, and 209 over S is equal to 17 over 1679 something. So rounded quarter is 3, 5, 1, 18, and 17, right? But still, this one, if you add all those rounded one, then what you get is 44 computers. So still 2 computers are remaining, right? Then again, by the Hamiltonian method, choose the 2 schools with the highest fractional part. So first one should be south side because 0.8321 is greatest among all other fractional parts. And next one is east side because, yeah, this 0.4786 is second highest among all other fractional parts. So the Hamiltonian apportionment is 3, 6, 2, 18, 17, and total number is 46. Right? So that's another example of Hamiltonian apportionment. Okay, is everything good? Or do you have any other question? Okay, then deal with next example. So several small towns were working together to reorganize their county representation. And there are 8 county seats and use the Hamilton method to distribute the seat among the towns. So here again, their population is, if you add all the numbers, then what you can get is 9,082. And the standard divisor is 9,082 over 8, which is 1,035.25. So the population and your quarter is 3860 population divided by S. So first one is 3.414019 something, and second one is 2.4823, and third one is 1.6569, and this third D has quarter 0.4404, and E has 0.0185. So rounded quarter is 3, 2, 1, 0, 0. But in this case, there are 2 seats remaining. So just choose the fraction part with the greatest fraction part. So in case C, and the next greatest fraction part should be recognized as B. So because B, 0.48 is greatest among all others. So Hamiltonian apportionment, they've got 3, 3, 2 seats in here. Because there are 8 county seats at a starting point. So Hannah's question is, why are 2 seats remaining? Because there are 8 county seats in here, but if we just round down the quarter, then we only give 6 seats for each town. So there are 2 seats remaining. So that's why we need to do Hamiltonian apportionment to assign those remaining ones. Does it make sense, Hannah? Great. So as you can see, if you know this quarter first, then Hamiltonian procedure is just simple, right? So I'll leave this 2.4 as exercise for you. So but in this case, what you need to do, the total number is 13,097. Then you can calculate your S as 13,097 or 100, which is 113.97. But I will leave it to exercise for you and fill it out in this Thursday. Okay, so that's Hamiltonian method. And then there are another method using divisors. So here we use it in the Hamiltonian method, we use standard divisors, right? But sometimes we can use the other ones, so called divisor method. Divisor method is just adjusting your divisor, the adjusted divisor D, to calculate an adjusted quarter, right? So instead of dealing with rounding quarter or not, just round the divisor first, then use the divisor to give some method, give some stage, right? So the first thing we can learn from this divisor method is called Jefferson method. And this is already, came from the Thomas Jefferson. I think you know who he is. So yeah, it is actually used from 1791 to 1840s, right? So the method is as, first of all, as the Hamilton method, compute the standard divisor first and compute the quarter max. And again, just round your quarter down. That's the similar to the Hamilton method, the same as Hamilton method. But in the number 4, if the total number of seats is not correct, which means that if there is some remaining seats, then call the current apportionment N and find the new divisors DI, which is PI over NI plus 1. And here PI is just I's population, a population of I states. And NI is just the current apportion of number of representatives just assigned for each state. Right? And assign seats with the state with the largest D and just repeat that procedures, right? And the last D I used with the used is the called adjusted divisor. So yeah, so instead of remembering all these steps, just let's deal with the same this Jefferson procedure to determine this high school problem. Again, we have 46 computers, and there are 5 high schools with the same population. So in this case, we know that standard divisor is 560 over 46. So it is 12.174 as a standard divisor. So if you just deal with your quarter, sorry, I also forgot to put the point in here. Sorry, then what you can get is actually the same as the previous one, because those procedure is the same as the Hamiltonian one until the getting quarter. So if you round the quarter, then what you can get is 3, 5, 1, 18, and 17, right? So that's the same as the Hamiltonian method. But here, if you just add or rounded quarter, then it only gives 44, computers to high school. So you have 2 remaining computers. Exist. So in this case, your DI it is population over NI plus 1. So first one is 39, which is population of north over this rounded quarter 3 plus 1. So it is 9.75. And next one is 71 over 5 plus 1. So 71 over 6, which is 11.83 something. And next one is population is 18, but 18 over 1 plus 1, which is 18 over 1 plus 2, 18 over 2. So it is 9. And next one is 2 to 3 over 18, because rounded quarter is 18, plus 1 is almost 11.74 something. And lastly, 209 divided by 17 plus 1. So 209 divided by 18 is 11.61 something. So in this case, you can see that the highest divisor is here, right? So it's for the south. So in the next apportionment, we just gave the south one computer. So everything is the same, but south computer which is came from which we given to south is changed to 6, right? Because we add 1 in here. And we can do the same thing again. Then 39 over 3.3 plus 1 is just same as the, here. So in this case, everything is same except south, right? Because their numbers are not changed. So here it is 975. And here it is 9. Here it is 11.74 something, 11.61 something. But only in case of south, their numbers are changed, so their DI is also changed. Now we use 71 over 6 plus 1. So it is 71 over 7, so it is 10.14 something. So at this point, now this 1174 is the next highest one. So by the Jefferson method, we just give one more computer on the west score, so which is 361, 19, 70. And then we just give all the computers to each school, so we are done. Right? So that's the Jefferson method. And then we call it the last D as the adjusted divisor. Okay. Do you have any question? Good. Let's deal with one more example. So let's return to the small town example again. So here we already have the 8 council seats in here. Okay. So in this case, again, standard divisor is already calculated, 1,000 something. So if you just use your previous population and quarter, then rounded quarter should be 3, 2, 1, 0, 0, right? So we know that only 6 seats are assigned to each town, but that's the same as the Hamiltonian one. But now we will use Jefferson's method, so we will need to calculate this DI. So here, first one DI is 3,862 over 3 plus 1. So it is 965.5. And in the next case, the population is 2,818 over 2 plus 1, which is 3. So it is 9.33 something. And the next one is 1,881 over 1 plus 1. So it is 940.5. And 500 over 0 plus 1, which is just 1. So it is just 500. And likewise, 209 over 1 is just 209. So the next apportionment should be go to A, right? Because A has the greatest divisor. So in the next case, it is adjusted with 4, and all other ones that get the same. So it is 7. And still we have one remaining 6, so you can do the same thing. So again, all other numbers are same except the town A, right? Because only apportionment of town A is changed. So in case of town A, it is 386.2 over 4 plus 1. Which is 5, is 772.4. So in this case, this 940.5 is the greatest one among all others. So the next one is 42200. A, right? So the next, the adjusted divisor is this 940.5. Right. So as you can see from this example, the pretty smallest states in the United States in the 18th centuries do not like this Jefferson's method because those small states D and E does not get any seats on this kind of method, right? But that's the first time when Congress adopt this one to distribute the seats of Congress, right? So, okay, do you have any other question? Okay, then let's deal with one more example. So let's return to this university case. So here, standard divisor is 113.97. So if you just calculate the quarter using standard divisor, then you got this number. So then rounded quarter is 42, 26, 29. Oh, will these tables be given in the exam? Yes, like in the last exam 3, I will give you a table so that in the workup part, you need to just fill out that table, then you're fine. So, and M is rounded quarter is 1. So again, in the Jefferson's method or Hamilton's method, all those rounded quarter is round down, right? So, and if you just add all the number, then it is 98. So 2 positions are remaining. So here DI is 5,565 over, sorry, 5,565 over 42 plus 1, which is 129.4, and 3 plus 71 over 26 plus 1 is 128.55 something, and 3864 over 29 plus 1 is 128.8 something, and 197 over 1 plus 1 is 98.5. So in the next apportionment, we need to increase the apportionment of the J because 129.4 is greatest among all other DIs. So it will be changed into 43, but all other apportionment is the same. And next DI, for K and L and M, their DI is not changed. But in case of J, each DI should be changed because now each apportionment is changed. So it is 5,565 over 43 plus 1 is almost 126.5. So it is, so now the greatest one is L. So by Jefferson apportionment, we need to add one switch to L. So the final one is 43, 26, and 30, and 1. So the adjusted divisor is 128.8. Okay. Do you have any question or anything else? Good. Okay, that's the Jefferson method. But this Jefferson method is definitely favored for large state, right? So Webster method is already, given for, actually used for House of Representatives in the 1842 to 1931. So, and in this Webster method, first of all, you need to compute the standard divisor and compute the quarter for each state. That's the same as Hamiltonian method or Jefferson method. But in number 3, round each quarter to the nearest integer. Instead of the rounding down, we just round each quarter to nearest integer. And in that case, so maybe there are some remaining seats that happen, but maybe there are some seats running out. So there are some seats which is greater than the number of seats of the house. So if you just count the total number of seats is not correct, then we use the find the divisor with this method. So if the number of seats needs to increase, then use this formula di plus, which is pi over ni plus 0.5. So in case of the Jefferson method, it is 1, and it's already added, right? But in case of Webster method, only if the number of seats needs to be increased, use this plus 0.5. But if the number of seats needs to be decreased, use this number di minus, which is negative 0.5. Then do the same thing as what we did in the Jefferson method. So it is just the same thing, but 2 different points is that first of all, we use the round to the nearest integer instead of rounding down. And second one is that if the number of seats is not correct, then we use the formula di plus or di minus for each cases, right? So let's deal with some example. Again, let's deal with this computer example again, because we already know what the Q is. So still we know the standard divisor. So if you just divide population by standard divisor, you can get the same quarter, right? So in the case of Webster method, rounded quarter is this, the nearest integer, right? So here, 3.2036 goes to 3, but 5.8321 goes to 6 because 6 is the nearest integer, and 1.4867 goes to 1, 18.31 something goes to 18, and 17.1670 goes to 17 because those are all the numbers which is less than the half of the fraction, right? So in this case, if you add all the number, then what you can get is 45 instead of 46, right? So here's the nearest integer. Then still you notice that there are one one computer is remained. So your quota needs to be increased, right? So in case of increasing, you need to use DI plus, right? And to do this, you can see that the first one is 39 over 3.5. It is 11.14 something. And 71, 6.5 is almost equal to 10.9. And in the east side, 18 over 1.5 is almost equal to 12. Actually, it is 12, sorry. Yeah. And 2 to 3 over 18.5 is almost equal to 12.05. And 209 over 17.5 is almost equal to 11.94. So by Webster apportionment, we need to choose the greatest one in this case, which is west side. So we just give west side one more computer. And that's done. So here, again, this 12.05 is the adjusted divisor. So in this case, it is very similar to Jefferson. Instead of adding 1 in the denominator, we just add 0.5, right? So that's the Webster method. Do you have any question? Okay, good. And then let's deal with next example. So again, this is the same example with this. So let's return to the small town. We're working together and we have 8 council seats and use the Webster method to switch among these, distribute those seats. And we know that these quarters are here by dividing population by the standard divisor. And by rounding quarters, still A has 3 because 3, 4, or 2 is less than 3.5, so it should be goes to 3 because here rounded quarter is just the nearest integer. And in case of B, it is 2, but in case of C, it should be 2, but in case of D, 0, in case of E, it is 0, right? So here you can calculate your DI. So again, yeah, if you add all the numbers in the rounded quarter, then 1 seat is remained. So we need to increase our quarters. So that's why we need to use DI plus. You wrote 18, but it should be 19. Sorry, Katie. Thank you very much, Katie. So it should be 19. Yeah, because 1 plus 1 increased, right? Okay. Okay. So in case of DI, here 3A62 over 3.5, it is almost same as 1003.43 and 2818 over 2.5 is almost same as 1127.20 and 8081 over 2.5 is 752.4 and 500 divided by 0.5 is 1000 and 21 divided by 0.5 is 42. So here the biggest one, DI is town B. So column B should have increased one, and the others are the same, so you're done, right? Oh, and this is the adjusted divisor. Okay, that's again the similar case with Jefferson method. Okay, do you have any other question? Then let's deal with this example 4.4 and just call it a day. So in case of this, let's return to the university's 100 student worker position. So use the Webster method instead of the Jefferson method. So here we already know what the quarter is. So rounded quarter for each carriage is that first J carriage is for 42 because 42.491 is less than 42.5. And in case of carriage K, it should be 27 because it is greater than 26.5. And for L, it should be also 30. And for M, it should be 2, right? And if you add all those numbers, then what you can get is 101, which is actually, greater than the size of position. So one position is should be removed, right? So in that case, we use DI minus, which is population of each ice group over the rounded quarter minus 0.5. So here, first one is determined by 5565 over 41.5. What I did is just 42 minus 0.5. And what you can get is 134.096 something. And next one is 3471 over 26.5, sorry, because I need to get rid of 0.5. And what you can get is 113.981. And the next one is 3864 over 13 minus 0.5, which is 29.5. And it is almost same as 113.983. And the last one is 197 over 1.5, which is 131.33 something. So here, when you need to decrease your seats, then you need to choose the number which is the, okay, so in this case, you need to choose the number smallest DI minus. So here, the smallest DI minus is this number, 113 point something, right? Because all other numbers are greater than this number. So by the worst apportionment, it should be 26, just get rid of one seat, and 32 to hold 100, right? So that's the Webster method with the case of decreasing. Okay. Do you have any other question? Okay, thank you for listening, and let's call it a day. If you have any other question, please let me know. Okay, do you have any other question, June people? Then I will close the session. Thank you very much.